Good afternoon, Aunties. So today in Maths Assistance, I'm going to be focusing on exponential equations, and I'm going to really just use and work through a few examples trying to cover pretty much everything that you need to know about exponential equations. Alright, so let's just start with something very, very basic. And in all of these questions, the question is to solve for x. Okay, so something really, really basic is 27 to the power of 2 is equal to 3 to the power of x. Now the intention here is to try and make our bases look the same on both sides. Okay, so we can reduce the 27 to make it look like it has a base 3 by raising that 27 to the power of 3. And then in the next step, we can use our law 3 of exponents, where we have an exponent inside the bracket and an exponent outside the bracket, to make that 3 to the power of 6 equals 3 to the power of x. And now that our bases are the same, we can equate the exponents. So therefore, x is equal to 6. Okay, let's look what happens when we have a fraction involved. So 1 over the power of 25 to the x is equal to 125. Now you should be able to recognize that the 125 and the 25 can both be brought down to a power of 5, okay, with a base of 5. But before that, the 1 at the top means that we can actually show the left-hand side, and this is again using your definitions of exponents, as 1 over 25 all to the power of x, because 1 to the power of x is still 1. Okay, and now the 1 over 25, I'm showing more steps than you need here, can become 1 over 5 squared to the power of x, and the 125 can become 5 to the power of 3. Okay, and now we've got a 5 in the denominator, but we want it in the numerator. So we can then use our definitions of exponents to bring that 5 squared in the denominator to the numerator and make it 5 to the negative 2 to the power of x equals 5 to the 3. And then once again, you multiply your exponents on the inside of the bracket to get 5 to the negative 2x is equal to 5 to the power of 3. And now that the bases are the same, we can equate the exponents to get negative 2x equals 3. And then finally divide both sides by negative 2 to get x equals negative 3 over 2. Moving on to example 3, we have 2 times 4 to the power of x minus 1. So the mistake that sometimes is made here is that you divide the 2 into the 8. You can't do that because the exponents are different. Okay, so what we do is we reduce each number, each base, 2, 4, and 8, all down to their prime bases. Okay, so remember, the 2 is already reduced, but that's to the power of 1. The 4 becomes 2 squared to the power of x minus 1, and the 8 becomes 2 cubed to the power of negative x. Okay, so in the next step, we can distribute the exponent here to the x minus 1 on the outside. So we leave the 2 to the 1, and then we get 2 to the 2x minus 2. And we do the same on the right. We distribute the 3 to the negative x, so that we get 2 to the negative 3x. In the next step, we can now combine the 2 bases on the left-hand side. Because they are equal bases, we can add their exponents. Alright, so we are adding the 1, the 2x, and the minus 2. So start with the 2x, and then 1 plus negative 2 is minus 1. And then on the right-hand side, we have to the power of negative 3x. So now our bases are the same, and we can equate the exponents. So 2x minus 1 is equal to negative 3x. Take the 3x over, so that the negative 3x, we add it onto the left-hand side. So 2x plus 3x is 5x. And we take the negative 1 and add it on the right-hand side to get positive 1. And then finally, we divide both sides by 5. And x is equal to 1 over 5. Number 4, very simple one, although it's sometimes students sometimes stumble with it because they don't know how to make the bases look the same. So remember, when you have a 1, and you can make a 1 look like any base you want by raising it to the power of 0. So here, obviously, we want it to look like a base of 10. So the left-hand side stays 10 to the x. We can express 1 as 10 to the 0. Okay, and now our bases are the same, so we can equate the exponents, and therefore x equals 0. Right, number 5 looks similar to number 3, but in this case we can divide the 4 onto both sides because the 4 has an exponent of 1 and so does the 8 have an exponent of 1. So because the exponents are the same, we can divide them. Okay, so we divide both sides by 4, it cancels on the left, and we end up with 16 to the power of x is equal to 2. Alright, and now we want to make the bases the same, so 16 becomes 2 to the 4 times the x that's already there. That gives us 2, and we know that that's to the 1. So now that the bases are the same, we can equate the exponents to get 4x equals 1. Therefore, x equals a quarter. Number 6, a little bit of a challenging one. So 3 to the 2x minus 2 times 3 to the x plus 1 equals 27. So you should be able to recognize that this is quadratic. Okay, and a quadratic, it looks a little bit different to what you're used to with a quadratic equation. But effectively, the format that a quadratic equation follows is that the first exponent, if you put it in standard form, is double the middle exponent. So if you think of a normal quadratic, you have an x squared, then you have an x term, which is x to the 1, so it's half of that first exponent, and then you have a constant. So here our first term is to the 2x, so we would want the middle term to be to the x, not to the x plus 1. So you're going to first manipulate that middle term so that we can split it up. So 3 to the 2x minus 2 times 3 to the x times 3 to the 1 minus 27 equals 0. So we're also equating to 0. Okay, and remember, this section here, we've used law 1 of exponents backwards, because if you had to work back from this step to that step, you would say that the bases are the same, so we can add the exponents, so we get x plus 1. Okay, but now that the 2 and the 3 both have the same exponents, because the 2 also has an exponent of 1, we can multiply the 2 and the 3 together. So we get 3 to the 2x minus 6, 2 times 3 is 6, times 3 to the x. We can't multiply the 6 and the 3 because their exponents are different. And then minus 27 equals 0. We are now ready to factorize this as a trinomial. So we're going to have our 2 brackets. And I always say the best is to first work out what signs you've got in the brackets. Okay, so because this sign here is negative, that means that we've got a plus and a minus. All right, so one of them has to be plus and one of them has to be minus. Then the square root of the first term, 3 to the 2x, the square root of that is 3 to the x. Because if you raise 3 to the x to the power of 2, you end up with 3 to the 2x. So we have 3 to the x in both brackets. Okay, and then we have to look at the factors of 27 that will give us negative 6. Okay, so it's negative 9 and positive 3. Okay, just before I continue, you can also do this with a substitution. All right, if you let the 3 to the x equal k, so let 3 to the x equal k, then you end up with k squared minus 6k minus 27. And then that's just a little bit more simple to factorize. All right, so same method. We know we have a plus and a minus because the last term is negative. The square root of k squared is k. And then our factors are going to be the same, negative 9 and positive 3. So that means that k equals negative 3 or k equals 9. Now because k is 3 to the x, we have then 3 to the x equals negative 3. And this will be invalid because we cannot get a negative. If we raise 3 to any exponent, whether it's negative, positive, or 0, we cannot get a negative. But for k equals 9, we would have 3 to the x equals 9. And then we make the 9 3 squared. Bases are the same, so therefore x equals 2. All right, continuing on the left-hand side, if we didn't use the substitution, we would have 3 to the x equals negative 3, which again is invalid. We cannot get a negative. Or 3 to the x is equal to 9. And then we do the same thing. 9 becomes 3 squared. Therefore, x equals positive 2. Number 7, we have 5 to the x plus 3 minus 5 to the x plus 1 equals 24. All right, now because of the negative on the left-hand side, we need to first simplify on the left-hand side. Okay, and the way we're going to do that is to use law 1 of our exponent in reverse again to separate the factors, and we do the same to the 5 to the x plus 1 and make it 5 to the 1 equals 24. All right, and now we have a common factor of 5 to the power of x. So we factorize that 5 to the power of x, and we'll be left with 5 cubed, which is 125. It always helps to multiply those out because there's no variables in the exponent, and it just makes it easier to work it out. All right, then we have minus, and in the right-hand factor, we have 5 to the power of 1, so that's just going to be to the power of, 5. Okay, and then we've got 24 on the right-hand side. Okay, so simplify this. We then end up with 5x, 5 to the power of x, times 120 equals 24. Now we divide both sides by 120 because we want the 5 to the x to be on its own. So 5 to the x is equal to 24 divided by 120. We can simplify that, 24 divided by 120, and that gives us 1 over 5. And remember, it's 5 to the positive 1 at the bottom. So we can bring that now to the top of the fraction so that we have 5 to the x is equal to 5 to the negative 1. Now that the bases are the same, we can equate the exponents, and therefore x equals negative 1. Question 8, 6 to the 2x over 9 to the x is equal to the cube root of 4. So here, because on the left-hand side, we've got two different bases and two different exponents. We can't manipulate them as they are with each other, so we have to focus on the numerator and the denominator separately and reduce to prime bases. So the 6 becomes 2 times 3 to the power of 2x, and the 9 becomes 3 squared to the power of x, so 3 to the 2x. And on the right-hand side, we can change from surd form to exponential form. Remember that there's an exponent 1 on the inside here. So the rule is you take the inside of the surd, the exponent goes at the top, so it becomes 1, over the number on the outside, which is a 3, so that becomes 4 to the power of 1 over 3. On the left-hand side, you now distribute that 2x to both of the terms at the top. So it becomes 2 to the power of 2x times 3 to the power of 2x over 3 to the power of 2x, and that equals, and now you can already see what's going to happen in the next step. The 3 to the 2x's are going to cancel. So we're just going to be left with 2 to the power of 2x. Okay, so the 4 on the right-hand side, we can reduce that as well to 2 squared. Remember, because we want our bases to look the same. So in the next step, we have 2 to the power of 2x is equal to 2 to the power of 2 over 3. Now bases are the same. We can equate the exponents. So 2x is equal to 2/3. And then lastly, we're going to divide both sides by 2. So 2/3 divided by 2 is the same as 2/3 times 1 over 2. And the 2's will cancel, so this ends up being a third. Another way of looking at it is that 2/3 divided by 2 is 1/3. Question 9 is very similar to this question 6, but I'm going to do it in a slightly different way, without using substitution. we can show the first term as 3 to the power of x all raised to 2. So 3 to the power of x all raised to 2. So that you can clearly see that it's a square. All right, and then we've got minus 2 times 3 to the x minus 3 equals 0. Okay, so there's a clear trinomial. We can now factorize that into two brackets. Again, because the sign of the 3 is negative, that means we've got a negative and a positive, two different signs. And the square root of this term, 3x all squared, is 3x. So we've got a 3 to the x there, and we've got a 3 to the x there. And then factors of 3 that give us 2, where one is positive and one is negative, gives us negative 2, is negative 3 and positive 1. So we have negative 3 there and positive 1 here. So that means that 3 to the x equals 3, or 3 to the x equals negative 1. And here again, this is invalid. There's no solution because, again, we can't get the negative. But on the left-hand side, this is 3 to the power of 1. So the bases are the same, and we can equate the exponents so that x is equal to 1. Question 10, we're dealing now with a negative exponent. All right, so negative exponents, when you factorize, are not your friends. So make the exponents positive. At the same time, you should be able to recognize by the structure of this that it's going to become quadratic. Well, it is quadratic, you just can't see it yet. So at the same time as making the negative exponent positive, we are going to bring over the constant. Okay, so the 3 to the negative x goes to the bottom and becomes positive. And we then take over the 4 and equate it to 0. Right, so now, at this point, we need to multiply every term by 3 to the x, okay, to get rid of the fraction. So this 3 to the x times 3 to the x will give us 3 to the 2x. But remember, we can show it as 3 to the x all squared. That just helps us with our factorizing later. Then when we multiply the middle fraction by 3 to the x, the 3 to the x's will cancel. So you're just left with 3. And then when we multiply 3 to the x to the negative 4, we get minus 4 times 3 to the x. Remember, you can't say minus 4 times 3 is 12 because their exponents are different. Okay, so now before we factorize, we're just going to put it in standard form. So 3 to the x all squared minus 4 times 3 to the x plus 3 is equal to 0. Okay, so now we're going to have two brackets and we're going to factorize. Okay, so this time the last term is positive. That means that both the signs in the brackets have to be the same. Either they're both plus or they're both minus. And this sign tells you what they're going to be. So that sign tells us they're both going to be the same because it's positive. And this sign tells us that they're both going to be negative. Okay, so we have two negative brackets. All right, and then the first factor, 3x all squared, the square root of that is 3 to the x. And then we need factors of 3, both negative, that give us negative 4 when we add or subtract them. So minus 3 and minus 1. Okay, so we have there negative 3 and we have there negative 1. Now we can equate both of them to 0 and solve. So 3 to the x minus 3 equals 0, but 3 to the x is equal to 3, or 3 to the x is equal to 1. There are no negatives here, so both will have valid solutions. In the first one, the bases are already the same, so we can equate the exponents, and x therefore equals 1. In the second one, remember whenever we have a 1, we can show that as any base that we like to the power of 0. Now the bases are equal, so we can equate x equal to 0. Last question for the session, question 11. 2 to the power of x is equal to the square root of 2 to the power of x plus 8 minus 64. First thing we do here is get rid of the surd. Okay, we'd rather that everything is in exponential form. So 2 to the power of x is equal to, and then root 2 becomes 2 to the power of a half. Okay, remember the inside number, exponent, divided by the outside number, which in this case is squared, and that's still to the power of x plus 8 minus 64. Okay, second step is we are going to distribute the half. So it becomes 2 to the half x plus a half times 8 is 4 minus 64. All right, and now just like we did, you should be able to start realizing that this is a quadratic equation because we've got to the power of x here, and then we've got half x. All right, remember we had x, we had 2x earlier over here, and then it was x there. So it's always half of whatever that first term is. All right, so in other words, we need to split that second exponent because we go on half x plus 4, we would just want half x. So it becomes 2 to the power of x is equal to 2 to the half x times 2 to the 4, which is 16, minus 64. All right, now you can see it's quadratic, so we're going to equate to 0. All right, so we'll bring everything over to the left-hand side. 2x minus 16 times 2 to the half x plus 64 equals 0. All right, so at this point, I want to show you if you did use substitution, you generally are always going to make this term in the middle, the one that has the exponent variable, as your substituted value. So we will say let k equal 2 to the half x. That means our expression will then read k squared, okay, because the first term is 2 to the x, not 2 to the half x. The exponent's double. So double a half x, sorry, double x is x. Okay, so k squared minus 16k plus 64 equals 0. All right, so two brackets. Because the last one is positive, the last term's positive, it means they're both the same sign, and the middle one's negative, which means they both have to be negative. So we have k squared, the square root of k squared is k, and then you need factors of 64, that's two negative factors that will give us negative 16, and that's obviously 8. Okay, so negative 8 minus 8 is equal to negative 16. That's your outers and inners, and then negative 8 times negative 8 is positive 64. So we actually only have one solution here, and that's k is equal to 8. And because k is equal to 2 to the half x is equal to 8, we can now make the base on the right 2 to the 3. Now the bases are the same, so a half x equals 3, and then 3 divided by a half is equal to 6. Okay, back to the left-hand side. If you didn't use substitution, you would need to know that when you square root any number, okay, so we know both signs are negative. When you square root any number with an exponent, you're actually just halving the exponent. So the square root of 2 to the x is 2 to the half x. Okay, so we have 2 to the half x there, and we have 2 to the half x there, and then the 64 again is the same thing. Factors of 64 that will give you negative 16 is negative 8 and negative 8. Same solution, except we don't have k. So 2 to the half x equals positive 8, which is 2 to the 3, and then your solution from there is the same. Half x is equal to 3, we equate the exponents, and therefore 3 divided by half is 6, and so x is equal to 6.